All right, I assume you can see my shared screen, I guess. Yeah, so this is week 6, and we're trying to address some additional topics. After last week, we talked about functions, and the previous weeks we talked about a little bit about data structure like lists, tuples, and dictionaries. And so you learned about branching and loops. So today we're going to put everything together and to talk a little more about how to iterate through those data structures, as well as some additional concept in functions, so especially recursions. Okay, so just to review, we talk about tuples. They are immutable. Lists are mutable. They are container type, and we need to pay attention to those details in terms of the caveat. Let's take a look. So here I have some examples. So here is the example of the list, right? Just a review. List is not homogeneous. You can have different types in the data, like string, integer, and even list of lists. Okay, you can use a pen function to put list element into at the end into the end, and you can also insert at particular index. But be careful that operation expensive in terms of number of elements is involved, and then you can remove particular element from the list, which is super useful when you are coding the text-based game. For example, if you have items in the rooms and you want to put into a list, right? And you can check the number of lists and number of elements in the list. You can also delete item from the dictionary or the list from the room, so you don't need to encounter it again. You can also use a pop method to do those things. It also has a sorted function. You can sort the list by its custom function, or actually if an integer, it knows how to compare stuff, right? And there's a special parameter, it's called reverse equal to true. That means you can sort it by a different order, right? Ascending versus descending. And there is also a method called from the list sort. Basically returns nothing, but it turns out to alter the original list in a sorted order. Okay, this key function, let me talk a little about. So it's basically, you can specify a special function, especially when the object is a custom-made object. We'll talk about these classes later. But yeah, if it's a non-traditional object, you need to, the computer don't know how to compare those objects, right? You need to give them a special function so they know how to convert that to a known quantity or object that they do know how to compare with. Okay, in this case, because string and numbers are different types, they cannot compare directly. So what I did is by converting them, if it's an integer or a floating number, I convert them to a string, and I only compare the lengths, so that that's unified, right? The method. So you can compare the lengths once you convert everything to a string, and Python do know how to sort them. Okay, so dictionary is empty dictionary is like a curly break, and it contains key and values, right? Key and value can be anything. Key needs to be unique, right? That's the only requirement. You can access the individual element by the square brackets, but instead of using indexes, you can use keys to access the value. All right, you can pop the item by the key, and you can get the key and value pair. Okay, you can print all the keys by the keys function, all the values or items give you the key value pair. If you run this, you can see all this result. And you can also use the get method to get the particular key. That the difference between the get method and just the square brackets is that if the key does not exist in the dictionary, the get will not throw an error. Instead, you can specify what's the default value to return if the key does not exist. In this case, I return a warning, no such key. Otherwise, it will have a Python will throw an error, says there's no key. You need to be careful about that. All right. So in that case, you need to check if the key, like say, for example, if this key in dictionary, right? And then you can just manipulate the keys. Okay. Tuples are immutable. You can have different type in the tuple too. Be careful when I say immutable. This tuple, the element itself can be mutable, right? Or can be immutable. And if you are given a reference type, what I mean is that if it's a like list inside this element, then the list itself is mutable. So it end up with you can alter that particular object because it's mutable. So it's careful about that. And we didn't talk about set because it's but it's super useful if you are you want the element in that container to be unique, right? So that will guarantee you a unique set. So that's overview of all the data structure we reviewed so far. Okay, and so let me switch gears, talk about some recursion stuff from the function side. So what is recursion? It's a way to, basically solve the problem by divide the problem into a smaller piece and conquer them a smaller piece and then gradually build up the solution. So semantically, recursion in programming means you call a function and call itself again, but every time you call the function, you probably will change some condition so that you won't end with an infinite loop, right? And so that's another way to iterate through the problems. You can also use a iterative way, but sometimes one way is better than another in terms of different measures. Okay, so give you an example. If you want to multiply a times b, right? In grade school, a times b means just add a b times, right? So a times 10 means you add 10a together. Okay, so iteratively you can have a for loop, right? For I equal to from 0 to a, and every time you return the loop, you just add b, or vice versa. It's a commutative property, right? A times b equal to b times a. It doesn't matter which one you want to add. Okay, so that's iterative way, and this is a function to call that. I use a while loop. Basically, you subtract b every time you add a until b is 0. Okay, so that's the iterative way. Now, recursively, now you can think about differently, right? So a times b is b, you add a b times, but you can also see as a plus a times b minus 1. So a times b minus is the smaller problem, isn't it, right? So every time, and then it also can be added as a plus a times b minus 2. And until you expand them more and more until you reach a times 1 or even a times 0. And then that's the base case, right? You can't simplify further. Then you just go recursive call back and solve the original problem. So to translate that into code, right? So we need a function call with take two parameters, and the base case is when you check if b equal to 1, which is the base case. You just return a because a times 1 is a. Otherwise, you can just say a plus multiple a comma b minus 1. So every time you reduce b by 1. Does it make sense? I can give you another example, a simpler example. So for example, you treat this as say you are in a list or a queue, right? Maybe from in front of a restaurant, the restaurant is super good and you have to wait a long time. You want to know how many people in front of you, okay? you're in a list, right? You're waiting in line. And how you do that? Well, you can get out of the list and count, how many people in front of you, right? That's iterative solution. However, you don't want to do that, partly because you don't want to, lose your position in the queue or whatever. So you have another way. If you can ask the people in front of you, right? Hey, what's your position? Well, the people in front of you probably don't know either. And what he do, he or she can also ask the people in front of him or her, hey, what position are you? And you can do this ripple effect, right? You can, hopefully all the people in front of you can do the same action until it reaches to the first person in line, right? And he has nobody in front of him, so he knows his position is what? It's 1, right? Okay, so he tells the people behind him, hey, I'm 1. Okay, then the people behind him knows, oh, I'm number 2. If you're 1, I'm number 2, right? Add 1 to your answer. And the people behind that guy will say, oh, I'm 3, because it's 2 plus 1. And all the way back, it turns to you, the person in front of you, he said, oh, I'm 100. Then you must know your position is 101. Isn't it? So translate that into code. Let me just like recursion dot py. Okay, so let me just write some generic, like my position, right? So we take parameter, I don't know, n. Oops. So so if n equal to, let's say 1, I don't know, return, right? Return 1. That's the base case, right? If I'm 1, else return my position given n minus 1, right? Okay, so print my position, let's say 10. I don't know, let's see, Python recursion.py. Let's see. So this has 1 plus, right? So you want to return 1 plus my position and minus 1. And minus 1 is the one before you, right? So let's run again. Sorry. So you can see your position is 10. Obviously, you don't know yet, but again, that's the illustrative. So let me put into python-tutor.com to show you how this recursive call is made. Okay, so let's put it here, visualize it. So okay, so now that function call, right? Wait. Oh, I had to include print my position. I'm the 10th person. So here you go. Initially, the function call with parameter 10, but I don't know how to deal with that. So I delegate that to my next recursive function call. It creates a new stack with parameter n minus 1, which is 9. Again, he don't know what to do, and he go again with another function call n equal to 8. You don't know. You keep asking, hey, what position are you? Until he reached what, 1, right? And I know I'm 1, so I return 1. Okay, return 1 and return 2 and return 4. So why? Because every time I return, I add 1 to it, right? And finally, I got 10, which is here. Okay, so that's the power of recursion, I guess. Sorry, here. That's a silly example, but that hopefully give you idea. There's another way, the example, factorial, right? Mathematical factorial is defined as n factorial is n times n minus 1 minus 2. So it's if you glance that, it's very similar to what the example we did in multiplication and the people in the queue. So you basically can treat an factorial as, let's say, factorial of n, right? And if n, base case equal to 1, return what? Return 1, right? Right, factorial is 1. Even 0's factorial is 1, right? So now else, so you can return n times factor of n minus 1, right? You just multiply by n, and it's like, for example, 5 times factor of 4 and times 4 times until it got 1. Okay, so let me just print factorial of 5, for example, right? And if I just run this, 120, right? So it's very, very quick. And of course, you can do iteratively fact either, right? Just the for I in range what? Range n, right? Result times equal to I. Right. First of all, result equal to 1 and return I. Right. So fact, that's using factorial iteratively, and just verify they're the same. Let's do 10 this time. 10. Okay. So run it. The better wait a second. Oh yeah, there's a simple bug, right? Range n is starting from 0, so you have a 0, so it's 1 to n, right? 1 to n minus 1. Wait, 1 to n. Yeah, 1 to n plus 1, because the n plus 1 is not actually, yeah. Sorry, comma n plus 1, right? And you reply that, so that will give you the similar answer. Same answer, actually. All right, so here you go. This is the iterative way, and this is the recursive way. All right. So again, you need to have a base case in recursion, otherwise you will not do that. And this is a breakdown of how a recursive function call is made. All right. So just remember, each function call has its own environment, local variables that's not affecting the other function calls. If you want to pass the value, you need to return something or pass in a reference. Okay, so so that's the two comparison again in this slides. So I'm gonna skip that mathematical reasoning. I guess there's tons of interesting problem that can be solved by recursion. I guess due to the interest of time, I'm rather, you know, I don't know. Shall we talk one more? If you're interested, we can talk about some more complicated problem. I will just show you a practical example. For example, you heard about sudoku game, right? Solving a sudoku game. Right?
Yes, sir.
So sudoku game, let me give you a sample board like this, right? You have a array and you want to fill in the numbers. Then there's a rule like each row have different number, each column has different number, and each box, which is 3 by 3, has different numbers, right?
Mm-hmm.
So how you can, so there is a sudoku solvers online, and how they made it, right? How they did it. So I can briefly give you some ideas if you are interested in using the concept of recursion. So here is the main function I have. Initial board is basically a list of lists, right? I use a list of lists to simulate a sudoku board, okay? Row, column, and this is a 9x9 board. Okay, and I'm gonna create a class that you haven't learned about, but again, it's just to make my code organized better. But yeah, I'm gonna just create a class sudoku, right? So the class basically a collection of functions. So I can put a function. This init function is a special one. We'll talk about in the last week. So basically, I will initialize some of the variables. Like I have the sudoku board, which is a list of lists. I can print. There is a print sudoku function because I want to know my current status, right? And there is a row is length of board. This is a typical configuration. I can get a length of the board, which is a row, number of rows. And then n is the columns, it's the length of board 0. The first row, how long that's a column, right? Okay, I'm gonna define a print function, print sudoku, so I can print it. Okay, sudoku, which is I'm gonna copy and paste because it's not interesting to you can do it too. So basically I print those symbols, right? Like what I did here for the first row, and then wait, try just tab, shift tab. Okay, so that's the print function. Self.board. Oh, there is a self here. Okay, so so basically I have a function to print out the sudoku. I guess I spelled sudoku wrong.
How do you know? How do you see this shit? He is down.
Sudoku, right? Sudoku. Okay, wait.
You gotta spell different.
Sudoku. All right, so finally we get it right. All right, so we can print sudoku. So let's just print it, just test it with, right? So you write some code and you just print init board. Well, actually, I'm gonna initialize the object, right? So I have a game is equal to sudoku and with init board. So I pass in the board and print. Actually, it's game dot print sudoku. So I'm gonna print the initial board, right? So I'm in recursion.py. Actually, I'm gonna change this name to sudoku.py. Okay, so I'm gonna run it, Python sudoku.py. Nothing happened. Oh, you know why? Because I haven't called this main function, right? So you have to do this like name equal to main, right? Have you thought about this? And you have to call main function. So now I can do that again. You can see I have this board printed. Why have two print? Did I print it twice? Yeah. Oh, I see. When I initialize Sudoku, I print once. Okay, so yeah, I did print it twice. Sudoku board. So I don't need this, actually. It will print it for me already. Wait. Game using Sudoku board. Yes, it will. So that's the initial Sudoku board. Now I'm going to solve it recursively. How? Well, I can think about it. Okay. This is where the solver. Okay, let's just ignore this. Let's see. I have to make sure that. So let's solve Sudoku, right? So it's a solve function. So how to solve Sudoku? First of all, I have to iterate through every single node, right? Every single slot. Okay, I have to iterate through. So the idea is iterate every slot. Okay. And of course, you have to, if it is empty, right? If it's not empty, then you don't need to do anything, just skip. If it is empty, then check if a number is valid, right? So you have to write a helpful function to say, hey, if I put the number 9 here, is that valid? So if is that, so you check the row, if it's unique in the row, if it's unique in the column, if it's unique in the grid, then it's valid answer, right? And then, every time you put in a new number in, that means you reduce the problem into a smaller problem, right? You reduce this board, you're one further away from the complete solution, and you keep adding numbers, okay, to valid numbers into those space. The more number you fill, the less number is a valid number you have for each position, right? So eventually, hopefully, you can fill out every type. That's how human does it, right? That's how human does it. So computer can do it very fast. That's just the basic idea, right? So how to iterate through the slot? Well, for row in range 9, so it's the board, right? Actually, we have the self.m, which is a row of the board. So we can do arbitrary size for column in range self.n, right? So that's a row and column. If not means if it's empty, right? Self.board of row and column. Okay, so that for that particular row and column, if it's empty, right? Not means, not empty, that's true, right? So it's true means is if empty, not empty is true. Okay, that makes sense. And then you're gonna try put in the numbers. I'm gonna put in all 10 numbers, right? To try it for number in range of 1 to 10, right? Oops. So 0 to 1 to 9, 1 to 1 to 9. 10 is not included. So what? If it's legal or allowed, okay? If you allow it to, so you put a number in and you give them a tuple of row and column. So basically, if the number is allowed in that row and column, right? If in this grid, then I'm going to assign this to the board. So by putting that number in, right? Because this is allowed, I'm going to put this number, assign that into a number. Okay. So I put in a number in, right? Okay, now here's the recursive part. So once I put a number in, I reduce that to a smaller problem. And this solve will return if it's solvable or not. If it's solvable, it gives you a true. If it's not, then it's false, right? So if I'm going to solve it again, actually self.solve. So basically, when you solve, we call this solve, what's the difference between this solve and the solve that you just did? This solve will have this board different, right? The board is now have one more number in than you previously. So you reduce that to a smaller problem. If that's the case, you return true. Okay. All right. So what if you can't, right? If you try all 10 numbers, this else means you try all 10 numbers, none of them works. That means you have a dead end. So no solution found for that slot. I'm gonna backtrace. I'm gonna just take that number out, right? By taking that number out, I mean I'm gonna assign that row and column to 0. Does it make sense? Because 0 means there's nothing in there. Okay, so I backtrack the number, and I'm going to return false because I know if you just put 9 here, it will not lead to an answer because I recursive call it, and I know that it's a bad move, just like a chess game or whatever. And finally, if everything is true, I make sure I'm going to return true, right? So I find a solution. So see this. Wait, I have one more. Okay, so that should be aligned with 4. All right, so that's the solve problem, right? And I'm gonna just run what? I'm gonna say if what? If game dot solve does it have a okay yeah, if game dot solve is true, then I'm gonna print sudoku again, so print the solution. Okay, so that's the idea. Now one thing I'm missing is how to define is allowed, right? How to define the number is allowed in that particular position, right? Number and row and column, right? That number. Okay. Of course, this is a member method, so self number and coordinate. Actually, I can make it a tuple coordinate. Okay, so how to define is allowed, right? So I'm gonna say row column is equal to coordinate. Okay, so I get a row and column, right? And what? We have to find which box, right? The number is in. So which box within the 3x3 row? Well, there's a nice trick. If you don't understand, that's okay. So I'm gonna say row divided by 3, integer divided and multiply 3, and column is column integer divided by 3 multiplied by 3. That will give you the top left corner of that grid. So I get R and C of that grid. Well, no matter what number is in this bigger grid, right? If number in self.board row. So if number in that row, right? What that mean? So the number is the number you want to put into that row, right? If that row already has a number, you return false. You cannot put in because you already have that number input. Same here. If number in column, well, I can have a list comprehension. Now, list comprehension is something that you probably encounter this chapter, right? So list comprehension basically says you have element I and column. So basically, for every I in range 9, so because I is a row, right? So for 0 from 9 0 to 0 to 8, and for each row, I look at this column only. If number in that particular column, then that was a false, right? So it's not in that column. Okay, so now it's left in, let me do else here. If number in that box, right? So the box is basically I and j, any location for I in range, let's say from top left corner row to row +3, right? There's 3 rows for j in range of top left corner column and column +3. So basically, for anything in that box, if the number is there, I'm going to return what? False, right? So basically, this 3 lines says, okay, if my number is already in that line, row, or in that column, or in that box, then this is not valid number. Make sense? If it's not, then it's a legal number. So else it's true. Okay, now I have defined this function. So basically the idea is, given a grid, I'm gonna keep solving it by adding a number to an empty slot, right? And the number choosing from is 1 to 10. And if any number is working, I'm gonna solve it again in the smaller until there's nothing to solve, and it will return true. Okay, let's run it. Game is sudoku. Oh, it's solved. Look at that. Beautiful. So that's the basic idea, power of recursion, right? You can see this idea is super intuitive in terms of like what human can solve it, but you just blindly trust, oh, it will solve to a smaller number and that. So that's the entire code for the Sudoku game. I'm gonna give you the link. So just interested that you can study that, or maybe make it a more better game. Because this is just a solver. You can make a GUI out of it, or web game. So, all right, what time is it? Wow. So we spent a lot of time on this Sudoku game, but I guess that gives you some interesting perspective of power of recursion, right? So let's talk about some. I don't have time for the dictionary. Well, I guess we can talk about the dictionary in the next class, right? List and dictionary. But do you have any particular topic that you want me to emphasize, like labs? I want to prioritize those things first. You can look at my videos on the previous term. It will also have a detailed, description on dictionaries. Okay. So dictionaries value is immutable. It can be any type. You can have duplicates, but the keys must be unique and immutable, right? Int, float, string, tuple, and boolean are legal. However, don't use float. Okay, why? Well, let me go back to Python shell, clear. So if using float, right? Let's say 0.999 0.99999 is equal to 1.0. Is that true or false? If you use these two numbers as your key, what will happen is Python will treat these the same. Okay, so don't use float because there is a rounding error, truncation error. Depends on how they because of how they represent the numbers inside the machine. Okay, so any other thing, integer, string, tuple, and bool are fair game, and dictionary will keep no particular order, so don't rely on the order it was inserted. It will probably be different after you do the deletion and pop. So, but you can always using key value to access to it. So the difference between list and dictionary, list is ordered, dictionary is probably not. No guarantee, right? Indices have order, so from 0 to a higher number. Index is integer, but dictionary, the indices can be anything. It's a key, right? Can be integer or can be anything, like string and tuples and such, even booleans. So a lot of application, typical application or the very useful application using dictionary, you can count the frequency of words in a text. Okay, so the idea is you have a dictionary of string to integer. String is the word in the lyrics, for example. Integer is the number of times this lyrics exists, the word exists in the lyrics, and you can find the word that occurs in the most, and how many times using a list in case it's more than one word, right? That has the same frequency. You can return a tuple for the words list and the highest frequency. And then you can find the words occur at least X times, like 10 times. And you can just say, hey, my top 10 frequent used words in the list. So here is some brief code on how to do that. Lyrics to frequencies. Lyrics is basically a text. You create a dictionary empty first. And for each word in lyrics, lyric is just a list of words, right? You take one from the list and you treat this as a key, right? If the key word is in your dictionary, right? This is how it goes. Then you just you tally that you take that word, you trace that value. Value could start with 0, or with any existing counting, and you just add 1 to it to up 1 vote for that word. If it's not, that's the first time you count a word, you just make that 1, right? It's the first vote. And then you return how many dictionary, right? Same idea can be applied to votes, okay? And then and then most common words, you get a frequency table, which is a dictionary. Then you can take all the values and you say the maximum word is the maximum of all the values. Makes sense. And I want to know how many words in that list has a top hit list. So in the frequency dictionary, K is the key, right? The key, remember the key is the words. And using that key, you can check the frequency. If the frequency of that word is equal to the most frequent, you can append this word to the list, and you can return this list of words and best frequency. So this code basically give you the top most frequently used words in that song. And of course, there's some more applications I want to mention that. But also in the recursion case, dictionary can be used as a cache. What I mean is, look at the Fibonacci number recursion, right? So this is recursion. Fibonacci number n is n-1 plus n-2. However, it's not efficient because to calculate Fibonacci 3, you have to calculate 2 and 1, and calculate 4, you have to calculate 2 again. So you have multiple cases that the same Fibonacci number is calculated again and again. Well, what if you can just cache that? Meaning, if you calculate 2, I save it to some lookup table, aka dictionary in this case. And if you encounter that 2, you can just look at the table first. If it's already there, I don't need to compute. I just look at the number. So that's a convenient way to save your time. So here in the Fibonacci number function, recursive version, I added a D is dictionary, and I pre-populate with some functions like Fibonacci number 1 is 1, 2 is 2. So I already know these two. And then I put into this function. So whenever you do the base case, right? If that Fibonacci number is in dictionary, then I just return that cache. Otherwise, I can just do the normal Fibonacci function. And once I'm done, I'm saving that answer to that list. Don't forget about that step. So next time I can expand that list and use that as a cache. So by doing that in a dictionary, you you effectively calculate that Fibonacci number very quickly, right? So in this sample, for non-cached version, Fibonacci 34 requires so many recursive calls, right? And otherwise, it only end with 65. So it's significant saving in time. So that's another use of dictionary. Dictionary has so many, even in the text-based game, you have list of dictionary to indicate your game, right? So any questions on the text-based game, or any question on the lab? Let me touch base on the game a little bit. Let's see. Where is it? Okay. I guess I can. All right. Yeah, I can add a function. Text-based game.py. Okay. So. So in text-based game, there's really two main functions, right? One is navigate the room. One is to pick items. So how to represent a room or rooms? Well, here there's multiple ways. The recommended way is to use a dictionary of dictionaries. The dictionary's key is the name of the room, and the value is another dictionary which has the directions and the name of the next room. So basically, it gives you a map of all the rooms for each direction that this room can reach, right? So by doing that, you literally create a map. Does it make sense? So once you have that, right? Once you have that, you can start the player in the starting room, which is the hallway in the example. So current, you can use a variable current room, for example, equal to Great Hall. Now you have to be careful. You have to match the case and even the punctuation exactly. Otherwise, you have a different key, and you get. And now you can show some instructions. This is the function that shows the user how to play the game. Okay, I can define the function here. Show instructions. Right, I can pass the. Basically, you just I just okay, there's a capital letter here. There you go. All right, so then you have a game loop, right? While true is a game loop. So basically, it will continue with the game until your condition met that you can successfully exit game. So what's in the game loop, right? First of all, how to break out them. If the current room, for example, is like exit, right? So you put the exit here. That's nothing to do with this room. This is not actual room. Then you can break. Or you can say if the condition, like you collect all 6 items, for example, right? And you can say move. You can get the receive move equal to input, right? You get input like the show me your move, right? So you can give them some prompt, okay? And the move is in the, for example, give the example, go west, for example, right? Okay, so it's a 2 word, and then you just ignore the first word because you know the go. Well, actually, don't ignore, but the goal is like, say, for example, move. I can change it to command. Command is move dot split. Right, you split that into a list. So if commands, for example, 0 is equal to go, right? Now, of course, user may give you go and go. So I'm gonna convert to lower. Convert to lowercase will guarantee that it's a lowercase, right? So you can deal with that. And if that's the case, and then you check commands 1 dot lower. Actually, not dot lower. Dot capitalize. Right? You can capitalize it. Equal to what? Rooms. Current room. So you know, current room represents what? Represents the current room's entry, right? The key, and the value here is a dictionary. So you have I'm getting the next directions. If that's in that direction, that means I can go that way, right? Then I will go that way, right? You need a colon. I will go that way. So current room equal to, I go that way by what? By changing the current room to whatever the direction is, right? If that's the case, I'm doing that. Set the current room to the new room. And if not, if the current, the value is not in that direction, so you can print, like you can go that way, right? Something like that. So give them user a feedback, right? And then this finish the command go. If user types exit, right? Then I know I can set current room to exit. Well, you may say, hey, there's no exit room here. That's okay, because here, I just put it as a special value signal that indicate, oh, it's time to end the game, right? So you can have other way to do that. And if everything failed, if there's no go or exit, then, because I'm only implementing the navigate, right? I can print invalid move. Okay, so you can then you go back to the loop and it will ask the user to do it again. Now, if you want to do it nicely, you can print some ending word like thanks for playing. Come back next time. Okay, so this is a pretty complete story. Okay, you have a game loop. You just keep passing the user command, and according to command, you can deal with user input, and then you go to the different part of the room according to this map, which is dictionary. All right, so any questions? I think that will do with the first part of the project, navigating room. And you can expand this to taking the item. You can put the item here, like for example, item and maybe sword. Okay. So then for each room, you can get item and then delete this after you get, right? And then you put this item into a collection like items. Use a list. Okay, so this way you can count, like you can even add you have current room or like, you know, length of items is equal to, for example, you have 6 room, 7, you know, 6, then you say you win, right? You can say you win. Anyway, so all kinds of ideas. All right, so we talk about recursion, function, recursion, and dictionary. I think these are 2 powerful techniques. We talk about Sudoku game that's using recursion and so on. So hopefully you can have some fun with these ideas. All right, any questions? Let me stop the sharing and stop the recording.